let us continue discussing all these operations with the second order tensor. So we just looked into how we multiply a vector by a second order tensor. So we have a multiplication of these two creatures. Now, next what we will do is we will look into the multiplication of two second order tensors. So let's say we have a second order tensor which is in fact will be a product for of two other arbitrary second order tensors AD. So we're looking into expressing the new second order tensor F in terms of the components of second order tensors A and D. So our next step here is rather simple. So we already know how to write each of these tensors in terms of their components and their basis, and so we can just go ahead and do that. So and then so you will see again, so this is standard way how we do that. One more time, I emphasize that it's important if we here used ij indexes, so we choose another a different set of letters here for the indexes. All of them are dummy, and it doesn't really matter which letters we choose, but important that we don't mix these indexes with those, otherwise we'll get lots of confusion here. Now, as the usual thing, already repeating that through the previous lecture, is our manipulation here is just to pull out everything that is scalar. So aij, we can just put out of the parentheses and solely deal with our with what is bold here. Basically, we're dealing with vectors, or the combination, the tensor multiplication as the tensor. And so again, so this could be written more specifically if we wrote put a dot here, so indicating that there is a dot product between this AD, meaning that there will be there will not so these two vectors will contract, so there will be contraction of these two, so there will be scalar product between EJ and EM, while EI and EN still will be written with tensor multiplication. So basically AD means that these neighbors, they multiply as a dot product. So let's write it explicitly again, putting aside A, I, J, D, M, N. But then what happened here is just we have a dot product between EJ and EM. So and then it of course becomes a scalar, right? And well, remind that it will be just Kronecker delta, but this is indeed a scalar. And what remained on the multiplication of these two tensors is just EI tensor product EN, right? So that of course makes sense. So we expected that this multiplication will lead to second order tensor, and indeed this EI tensor product EN is the basis for the second order tensor, and all these that we need to deal with is the components of that second order tensor IN. And at the end we expect that the components here will have the indexes of IN to match these for of the basis vectors of the dyadic product. Now, so EJ.EM is nothing but Kronecker delta. Again, if we don't remember that, we can go take it the long way and multiply them, and then recall that they are mutually orthogonal vectors, unit vectors that when projected upon itself, that will be unit, will be 1, and it's projected on their perpendicular neighbor that will be 0, and hence we'll have the diagonal matrix 1 1 1 0, or we specify it as a Kronecker delta, which is 1 when J and M are the same, and 0 when J and M are different. So this is Kronecker delta, and we remember that with Kronecker delta we can take one more step. We can identify which index is repeated. For example, you can say that you find M here and M here, so that delta Jm acts on dmn, and just simply replace that M with J, and then the result will be Aij, and here djn, right? And so if just we cut what was in between and just repeat FAD, so the result is that we have Ij djn, and that will be fin. And you can see that here again, so just to recall, so the I and n, right, so these are the free indexes. These are the free indexes in this index notation, and jj here is the repeating index. And so in in this index notation here for the components, so we again have this summation here over jj. So if we want to write these components, and so then we'll have a summation, we'll have these terms of jj repeating for each I and each n. There will be a sum of 3 of these running from 1 to 3. Right, and so that also can be written in the index notation like that. And this is, okay, again, fin, so these 3 indexes here on the left hand side, and we expect the same 3 indexes to be on the right hand side, and indeed we have these 3 index I and n here, and they don't repeat, and we have this j and j here, they don't repeat, right? But these components, that's already not the tensor, so we're looking just at this part of our multiplication. And for components, then we can use this machinery of the matrix multiplication. That basically what you also do probably most likely in MATLAB. So when you have the one matrix 3 by 3, and that is a result of multiplication, one matrix 3 by 3 and the other matrix 3 by 3, so these components do multiply exactly like that, and so that is what you would obtain here. And as you start multiplying that, you indeed will see that each entry in resulting say f11 will have this summation of I1 dn will be I1 j djn, and so there will be and n is also 1 if we want f11, but jj will be running, so we have a11 d11 plus a12 d21 plus a13 d31, right? So that's that will be f11. Again, you can just multiply this with the corresponding column and obtain this result from here, right? And so this is with that. So this is how we do the multiplication. Basically, when you see, so we write f equal ad, we mean that so the bases that are neighboring here, they contract, they multiply. So the dot product is between these two neighbors. Okay. All right. So then next. Then next we are going to our double dot contraction. This again, this is just the rules that we agree upon to use as we define our language, how we'll treat this matrix, these tensors, when we try to manipulate them, multiply and create new tensors out of when we describe physical laws. But now again, this is just a language, can be defined otherwise. Nevertheless, so next important operation is the so-called double dot, right? So we borrow this dot product from the situation when we have two vectors, for example, and just projection one on another. But we have higher order creatures, and actually sometimes it would be more important, actually useful for us to have a double dot product of this. And so interestingly, when we write the double dot product or contraction of two second order tensors, the result of that is that we produce a scalar, and that is similar to vectors. So for vectors, to shrink them, to contract them into a scalar, so we just need one dot. So these are second order tensors. So then here we have double dot contraction. What does it mean? It means that we come and say, so now there is a dot product between this component EI and EM. So these two are paired. So there is a dot product between I and M, and there is also a dot product between J and M. And and again, this is just now our agreement. So we say, okay, this operation will be useful for us, so let's define it in this way. Now, if we said that it will be IM and JN will be paired, so there will be dot product between each of these pairs, so then we can again just pull out all the components here, the index notation outside. So AJM, DM, and then pair these that we promised to be our definition of a double dot product is EI, EM is a dot product, and EJ and EN dot product. And by now we already don't need to recall where it comes from the projection these based unit base vectors. So this is the definition of our Kronecker delta. And so we just can go ahead and replace them as deltas, and then distribute these deltas between where we want to replace the indexes by using the property of the Kronecker delta. Right? For example, I can take this delta Jn, and I can choose that this delta Jn acts on dmn, because there is a repeating index mn here, n and n here, so I can replace this n with j, or I can do this. I can notice that there is also j that also repeats here, and I then can repeat this j with n. But it doesn't matter in both cases. The result of that will be that we will create a dummy index here and here, so they will be the same, regardless of whether we decide to use a delta gn on dm or aij. Just a simple manipulation. And the same thing here. So we also create a dummy index of between here of the first indexes in A and in D. Right. So we could choose to do it in this way, or we could do it in the other way. So let's say that we paired aij with delta im. So we can so these all scalars. So we can do that. So there's no difference in the order of how we multiply. So delta im goes in here, for example, and we replace I with m, so the result will be amj. And this delta gn, so we decided just to put it together with mn, and noticing that n is repeating, so then we can replace n with j, and so the result is dmj. And so then we can notice that this is nothing but so amj, dmj, and all these that were bold, right? So all these e's that were here, they disappear. So this is the result of this double contraction. So there are no tensors, no vectors anymore. This is just a number, right? So this is a number so that will be a long sum, right? So that will have all the components for m and j that will run from 1 to 3. So there will be some of these, but there will be absolutely no vectors, and there will be absolutely no tensor. So this is just a number, it's just a scalar. Okay, so again, double dot of AD is this rather long sum of this of the components that are written in a certain way. Actually, you can see that you have the repetition of this M and J here. So as the indexes, as the summation goes. All right. So now with this, so we introduce a double dot contraction, and similarly, there is some analogy to what we did for vectors in the scalar scalar product or dot product. Is we use that to calculate the projections. For example, we took any vector and multiplied it with dot product with our basis EI, and then we obtain the components of the tensor. We can do the same thing or similar thing with our second order tensor, so to obtain the components. And so now we are going to produce this double dot contraction operation. We will act with our dyadic basis EI, tensor product EJ, multiplying any tensor, some random tensors that we want to obtain the components. Right, so this is our tensor, right? It doesn't have any components there, so the components are just single unit. It's one, right? And this is the tensor, our random tensor that can have any components that we will call them Aij. Also, at this moment, I and J are taken here, right? So to avoid any confusion, so in this A, we will use different indexes. So it's very common to use MN or KL or things like that in these notations. And so now, so we keep this I and J here, of course, and then we write so we have chosen to have M and N combination here. So again, this is so these are repeating, they are matching, right? But so they need to be different from these two. We cannot choose IJ, otherwise we will get into a very confusing situation very soon, right? So for example, so now we are going to multiply EM and EI here, and and if we have chosen here by mistake to use IJ, so then we would need to produce scalar product of EI and EI, but that would be exactly the same thing. So that will just a summation of this that will produce a number actually exactly 3, and that will not be Kronecker delta. That would be a different thing. So that we should avoid such situations. So that will not produce the results that we are looking for. Will not produce the components. Now here, so so we have chosen in the correct manner the indexes. Again, I just need to make sure that they are not the same, so to avoid the situations. That's all. So and now we said that the double dot contraction, we just defined it to be in the way that when we see the sign, we mean that these two, the first ones are dot product connected, and the last ones are also in the connection of dot product. Now, and so we just pull AMN outside and pair this I and M exactly as we have done just previously here, and so we can do it really very straightforward. So again, this is delta IM, this is delta JN, and then with these deltas, we just find this I and M. So we just find that there is an M that repeats in here, so we can use the property of this Kronecker delta and replace that M with I, and using this delta to act on this N and replace that N with the remaining J here. So the result will be just a IJ, right? So that just I copied this thing here, replaced the dot product EI EM with delta IM, and and put it here, and this product with delta Jn, and this is of course Aij, and of course the answer, the result is trivial. So the components of A are indeed the components that we Aij. So these are the components of the matrix that correspond to our projections on the dyadic basis. So you may not really visualize that as nicely as for vectors what the components would mean, but again you can return to something that was really the example that was used a lot in your previous courses in mechanics of materials, of the stress components, and then that would be very, very good visualization and the image of what this component would mean in the physical world. Now, with that, we will actually use this operation of the double dot contraction or projection of a tensor to define a rather important property of the so-called positive definites of the of a tensor. And so there's one more example that we're looking at is at the projection of a new tensor of that was a result of the before we go to the next topic. So there's one more example that of course we can calculate also the projection of AB and of a new second order tensor that is a result of a multiplication of two second order tensors AB. So that in our previous case it was new tensor F, and of course if you do the this exercise properly, then you're supposed to end up with the components of that new tensor being like this: I, K, K, J, and again the free indexes I and J here correspond to these projections, and their dummy indexes K, K. So you should try to you can practice these two examples together that from the previous consideration of multiplication of the two second order tensors and calculating their components by projecting them onto your dyadic basis. Now, okay, so now we are going to take our double dot product contraction and consider any random tensor and define it rather important properties of positive definiteness. So is it positive definite or negative definite tensor? And so you'll see that will be important for certain things like, for example, eigenvalues, problems. Certain properties will be ensured if we can ensure that the tensor is positive definite, right? So and again, so it's in many cases it's important, right? So in the for example, we would for a scalar we could think about the whether the value is more than 0 or less than 0, and can discard, for example, certain results on physical basis, as for example for negative or positive energy, right? So we can agree that we work with energy that only positive, but again for for the vector we can think about some other metrics such as length, and I can impose something like that. But I want to connect this negative and positive consideration also to the second order tensor here, which so the second order tensor is not directly defined by any number, although it has some properties, so-called invariants, and we will talk about them, that can be put in as just scalars and can quantify the properties of the tensor. I'm talking about the second order tensor now, and but so here we will define, without going into much length and discussion of that, this property of being positive or negative, positive definite tensor. And so if so basically we say it in this way. So if a tensor, let's say it's a random tensor A, if the projection of the tensor of a pair of any vector or on another tensor, again this is defined very similar to our direct product of basis vector. So here, but we are saying we can have any vector v, and so if such projections on that vector, that is the only limitation we put on here is that v is not zero. So if for any v this value, this double contraction, this projection on that v-based tensor will be positive or zero, then we call it semi-definite tensor. And of course, this is not a strong inequality. We can make it a strong inequality and divide that the thing. So now, because so it's the same, we don't have a difference here in this tensor v tensor product v, so we can just write it a little bit differently. So in particular, we can just write it as through the dot products here. So A multiplied V, and we know that, and this is our another agreement, that we second order tensor multiply vector, and we don't specify anything else. So it's just a dot product, and this reduces to a vector, and then vector multiply dot vector V. And again, for any V that is not zero, we require it to be more or equal to zero, so we call it semi-definite tensor. And we can just call it positive definite tensor when the following property. So we'll just replace it with this strong inequality. So again, it's important to say this word. So we are leaving it here as, again, on the introductory level, not going deep into the details of the properties of the tensors that are associated with that at this point, at least. And that's just another illustration. But don't be surprised if when you see these properties considered so for tensor. By the way, in certain analysis, this such type of can be connected also to physical examples. For example, the stability of a wave propagation when you have any, for example, acoustic tensor, and that defines a condition for elastic wave propagating through materials when such inequality is ensured. But again, not in this course we will not be going into such details here. All right, so now we're going to define a special case of we're not talking about just a general any tensor, so we'll look into possible cases what can be, and our next guest is the so-called second order identity tensor. And so you actually have seen already mentioned that it is based on our Kronecker delta, so delta ij, and of course you've seen that in the MATLAB manipulations, or when you had the manipulations with matrices, so you have identity matrix. So in a way, this is similar. So now let's see how it is written or defined in as a tensor. So second order identity tensor. All right. So first of all, this is a symbol. In some literature, so this is a bold unit here, bold 1. This, however, can be in some literature, it's more popular to just have a bold capital I for the name identity tensor. And in many books, actually, in the Holzapfel book, you will see that I recommend for this course, you will see I. So, but this also is a possible definition for that. Okay. So, what does it mean? So, basically, this identity tensor, again, the component. So, if you think about this as a components as a matrix, so you will have one sitting only on the diagonal. So, now you can see that because delta ij has only components that are non-zero, actually one or unit, only when I and j are equal. So we have only three components here of this tensor, right? And that will be e11 plus e22, this linear combination, and plus e33, right? So all others will be zero. So that is the components, because the components of say e12 or e13 or others that are not non-diagonal, that will be zero. And these who are on the diagonal in that matrix will be 1. So these components are here. So, okay, of course we don't need to write ones here. So this second order identity tensor has an interesting property, which is you can easily see, is such that if you multiply it with from the right or from the left, any arbitrary chosen second order tensor, the results will be the same. So we will just return to the same tensor A, right? So we can multiply that tensor A with the identity tensor from the right, or we can multiply it with identity tensor from the left. The result will be again, so it just returns you exactly the same tensor A. It's a general formula that will hold true, and you can easily show it by actually writing the components of A and multiplying with I and doing all the proper second order tensor multiplication as we just described it just 1-2 slides before. Now, an interesting, an important property that also can be connected, can be also written in terms of our, for example, dot product or double dot product, or multiplication of I and A in different manner. So that in that way we can define the property, a certain number, a certain property of any arbitrary chosen tensor A. It is called trace, and you also encountered that in the matrix manipulation. So this new quantity for us, trace here, not entirely, but for tensors that is new, we introduced now. So you use that for the matrix. So basically, what you're doing, you're picking up some of the terms on the diagonal of that matrix. But what does it mean for the second order tensors? So it's defined in this way. So we can define it as a double contraction of identity matrix acting on A. So it's projecting on I, right? And then the result of that will be that we'll have this A ij, and then you can look into what we have written before. So if instead of this I here or identity matrix we had B, so the result of this double trace, when I have this multiplication, double contraction or double dot product, so that will be just a number, right, with the repeating indexes. So we would have Aij multiplied by Bij. So but now instead of B we actually have delta Ij, and as a result, so that what we will have here. So but now you can immediately say that look, that delta ij, we have a rule for that Kronecker delta, that if I see the index that is also exceeding delta, I can come to that index and replace it with the other index. So for example, I noticed that for whatever reason I decided that j is repeating one, so I is the one that I can replace this j with. So what in the end, so what I have is aii, but then this is nothing but this summation, right? Again, we're using this Einstein rule or summation rule. When we see these repeating indexes, it's nothing but the summation over that index. So we have the sum of these three terms, a11 plus a22 plus a33, and so this is basically a number, a scalar. So a trace of a second order tensor is defined in this way and produces a certain number that is based on the sum of the components that were on the diagonal of that matrix that build these components. Now we can also look into our tensor, second order tensor, which was a result of the multiplication of two other second order tensors, and then we can use a certain combination, so we can see how the trace can be written for those in terms of double contraction. Now let's write this this trace of again. So this is so a multiplied b is both the second order tensor, so the product is going to produce another second order tensor as the components that are expressed in terms of the combinations of the components of a and b. Alright, so now the trace of that new second order tensor would again be something similar to what we had here, and then we also expect that there will be some properties so we can expect that the multiplication that identity matrices acting on A will we can use the property to produce the same tensor, but it appears that actually the trace AB cannot be written like that. So there will be something very similar, but not exactly the same. So the trace AB will not be the double contraction of A and B in this way. There's one little trick that we need to change in this relationship to make it right. And it appears again can be shown that what we need to do, we need to make this right, we need to transpose either B here or A here, and then that will represent as a double dot contraction. That's again something that we can easily show by looking into what this double contraction will give us of these two. So this will be the difference of what indexes we exactly match there, right? When we multiply in double contraction, we basically come the first index here multiply of the components will multiply the will be coupled with the first index here, and the second index with the second index. But when we multiply A and B in this manner, or for example in this manner, so the indexes that are matched will be the second of A and the first of B. So this will be matched, and then when we do the trace of those, so basically the result will be II. So the first and the last one of these indexes will be matched. So this is actually a good exercise that you could do to practice all the materials that we learned so far with these new operations of double dot contraction and multiplication of the matrices. The one what we need to define properly, which we didn't yet, is actual transposition of the tensor. Again, this is a trivial operation for the matrices. We already mentioned that, and of course you already use that when you play it in linear algebra with transposing matrices. So it's standard, very standard operation. All right, but what does it mean? Also, there are some similarities. What does it mean when we do the when we write B transpose? What do we change? So that's our next topic is the transposition of tensors, of second order tensors, and basically so. All right, so we put this. So our notation is that. So we put this t here, and we mean that will be transposed. Now we can write the original, the whole tensor with the components and the dialectic product here, and transpose here. And as usual, we can just pull out a ij here, and we transpose these two. So we change the order here of this multiplication, so that becomes a different thing. Also, the components remain the same, but they correspond to the opposite one. So this I is now doesn't correspond to the first one, but it corresponds to here because I appears here, and j is corresponding to the second term. But these I and j's are just labels, right? So we can write it in a form that we like. So the only thing that we need to care about is that they're matching. So if we change, for example, this j and I here, we must change j and I here, and then the result will be that we have AJI, and that's our regular basis that we usually use to write. So in a way, so what we've done, yes, so this is the transposition of the components. So we can take that matrix and transpose that, and so that will be the transposition here. Now again, a very similar way how we treated before. So now let's complicate the game a little bit, and let's take a new second order tensor that is obtained by multiplication of two second order tensors, again that AB guy. Okay, so and then we'll want to transpose that. So it appears that there is will be a little bit of a trick in between. So we cannot write this so just put the transpose on A and B and say drop the parentheses and drop the whole transpose thing. So it appears to make it right. So there is one more manipulation that you need to do to make it actually correct. And suggest that here you can pause this video and write on try to derive what will be the results of this transposition based combining the previous exercises on multiplying the two second order tensors A and B, obtaining the new one, let's call it F, and then transposing that new tensor into in the manner that we just did for the tensor A. And so after some manipulation, you will arrive into the components. Actually will look like that. To make it right, you need to not only transpose each of them, but also change the order of them. So that only then that will be the correct answer. Okay, and so this is quite important if you see this first time, to try to practice that and see it yourself, or to and at least remember not to forget, because otherwise you will get incorrect answer when you do this manipulation in general. So there may be trivial cases for which you can get by without doing this entirely properly, especially if we don't have any entries that in the components that out of the diagonal. So if everything is simple, though, they may get off even with that. So now, so we define this transposition, and that allows us to define, to actually to look into certain aspects of the behavior of these tensors and identify, look into things that are symmetric and that are antisymmetric, or sometimes called also skew parts of the tensor. So we can separate each tensor into these two parts, right? So in general, any tensor would have that. So any tensor can have the symmetric part and the antisymmetric part, right? So the symmetric part, for us, the definition will be that basically, okay, we define it this way. So even so, there will be A plus I transpose and the coefficient of half. So that will be exactly the same as we take this A and transpose that, right? And that of course makes sense. So if you go ahead here, so that automatically will satisfy. If you transpose that, so the transpose of transpose will just drop both transpose, and that will be T here. But here we'll have transpose, but then again we'll have A transpose plus A, but that's exactly the same as A plus A transpose, so nothing unchanged, right? Now for the antisymmetric part or skew part, so we now that will need to be such that when we add the symmetric part in here, so it should be such a term that will produce automatically the whole A, right? And the only way we can do that is that we'll have the same term but negative, so because that's what we basically added to that quantity, right? So then when we take that all back and put it back here, this and that symmetric and antisymmetric part into this summation, so we'll have half A and half A that will produce us back A, and these two will eliminate each other. And so and the transpose of antisymmetric part will be the minus of this one, of the original one. So it will not be exactly the same, but it will be negative. And you can see that by basically trying to transpose this A skew original one, and when you transpose, so the result will be again half, factor half, and then we'll have A transpose here, right, minus A, because transpose will just drop, and that will be A, and that will be minus of your original result, which is A minus A transpose, because if you transpose that, we will have A transpose minus A, so that will be exactly minus A transpose. Alright, and finally, let us introduce another important operation after we have the transpose, is the inverse tensor. So this is important, right? So when, especially when you when you dealt with the matrices, it was important to have to be able to obtain an inverse matrix when you want to solve, for example, a system of equations. And so the definition for us in tensors will be like that. So the inverse tensor is such a tensor that by multiplication of the original tensor, either from left or from right, will produce the identity tensor. So this is a definition, and this is also always a check for us whether that will work, that the inverse tensor that we calculated is indeed the inverse tensor for our initial tensor. The check is take that tensor, multiply it with A, and see if you obtain the identity tensor. So now, as an example, we can go back again to a little bit of non-trivial example of our second order tensor, which is the multiplication of two other second order tensors A, B, and put the inverse out of the parentheses. And now to ask how can we open the parentheses and how that inverse will apply on tensors A and B. So And again, we need to now to actually to get to the right answer, what we will need to do, we will need to use this property. So you will need to take that IB minus 1 and make sure that when you multiply this tensor AB, the result will be the identity tensor. So and let me just maybe help you with this a little bit. So what you want to take your AB, the original, and multiply it with this AB minus 1, and you want to obtain the inverse. You want to obtain identity, and right, so that must be identity, right? And so if I now put that, just come in the parentheses and put here minus 1 and minus 1, that will not really work that well. But what will work is that when I also replace this in this way, so that will be, I will also change the order, then that will automatically produce the identity matrix, and you can already see that, right? So you still have this A and B, and why this combination is already the the identity matrix is because this whole thing is automatically identity matrix, right? It's a definition. You take the inverse, multiply it with the original, so this identity, and then this identity can multiply as B, and that's our definition of identity tensor, is that it doesn't change it, so that will be B minus 1, so it's still here, right, multiplying B. And it's again our definition for the inverse tensor, that multiplying B minus 1 multiplying B will be identity. So when you encounter this situation when you need to invert these two, and I apologize for the not perfect font here, but hope it's still recognizable, is just you alter the inverse of that. If you want to write it in the component, will be it will be also the change in the order of the multiplication, in addition to inversing each of these components. One more thing to say about it, of course, very similar to the matrix manipulation, we also need to make sure that the determinant of the tensor, of the second order tensor, is not 0. Otherwise, we will not be able to calculate the inverse tensor. It will be problematic. It will not be well posed problem. All right, let's us stop at this point, and we'll continue consideration of other important properties of higher order tensors, of second order tensor next. See you then. Bye.